Like, there's a bottom tray that pulls out there.
Oh,
Is that what you need?
strong.
Okay, so the one thing on this list here that I did skip is our last topic. It's called Faraday's Law. We would have talked about Faraday with a couple of you guys in physics last year, so maybe you'll recognize this name. Basically, this topic here has a bit of an overlap with physics in that we're going to talk about a unit of measurement called a coulomb. And I brought up coulombs before because I wanted just to put a bug in your ear so you remember the term. A coulomb is basically a lot of electrons. Rather than counting electrons by ones or by 12s, we just count them by a big number of electrons. Does that make sense? In chemistry, we also have a similar concept to that. It's called the mole. A mole is 6.02 times 10 to the 23 atoms. Unfortunately, for various different reasons, as science was developed, scientists weren't consistent between disciplines because it sure would have made things nice. It would have been nice if a mole of electrons was the same as like a mole of atoms. But unfortunately, electrons are measured by one set of groupings, and atoms are measured by another set of groupings. And so that's where Faraday came in, is he was the guy who was able to figure out a way to link how many electrons are in a mole based on like this concept of a coulomb. Does that make sense where I'm going here? So, I got a whole bunch of writing on this slide. Maybe I'll come back to that one because I think this is the one I want to work with first. So, I've mentioned the term current already. Current is basically how fast your electrons are flowing. Current is measured in coulombs per second, which is amperes. So many different units you got to memorize. Amps are written in A, and A is a coulomb per second, and a coulomb is basically a crap load of electrons. Rather than measuring them in 5s or 10s, you're measuring them just in a lot. Did I tell you how many were in a coulomb before? I'm sure it's written down somewhere. It's on a data sheet somewhere if you need to look it up. No, this is how many coulombs are in a mole of electrons. Because what I was thinking is how many electrons are in a coulomb. So you're a little ahead of me though. Okay. Anyways, one of the formulas that you guys aren't going to need to use, but is a physics formula, is that the amount of charge that occurs is how much coulombs you have times by time. Okay. If I stands for current, and current is measured in amps. I'm sorry if this is really confusing with the number of letters that are here. Maybe I should put it at the top. I is the official symbol for current. Current is measured in amps, which is an A, and an amp is a C over S. Does that make sense? So I is the symbol for current. Current is measured in amps, and an amp is technically a coulomb per second. And a coulomb is a lot of electrons, basically. Okay. So the way this formula works is if you have a coulomb per second and you times it by time measured in seconds, can you guys visualize how the seconds would cancel? And that would tell you how many coulombs you have, which is basically how many electrons flow. So this is actually a physics formula, so you don't need to worry about this one, but that just kind of gets us started. Long story short, Faraday was the guy who managed to figure out how to relate a mole of something to a coulomb. Because a mole is a whole bunch of atoms, 6.02 times 10 to the 23 atoms. A coulomb is a whole bunch of electrons. He figured out the ratio between the two things. And so here is the number that he figured out. There are this many coulombs, which is basically a whole bunch of electrons, in a mole of electrons. This number, by the way, is in your data booklet. So you do not need to memorize it, but we're going to use it quite a bit. The number is found on like the second page turned in. Like there's you know where all of those values were for C values for like air and water and styrofoam? I think it's in that table there. So don't worry about memorizing this number. But basically this helps us convert between a whole bunch of electrons and moles of electrons. Okay, here's our formula. This you need to memorize. Unfortunately, they don't in chemistry. They don't give you any formulas, so I can only think of really about 4 that you need to know. One is Q equals MC delta T. This is one of the next ones, And then the other ones that I'm thinking of involve the acid-base reactions. You guys remember the formula like negative log of a number? Those ones you'll have to memorize too. But write this down somewhere and commit it to memory. So if you want to figure out Ne, that's the number of moles of electrons, you need to know how fast the electrons are moving, because that's the speed of them, that's the current. You have to know how long the cell has been running for, so you need to know time. And then F right here is that Faraday's constant. And what it does is it flips things from coulombs, which is more of a physics unit of measure, to moles, which is more of a chemistry unit of measure. So that's what F is for. Current, how fast they're traveling. Time, how long you let the battery run for. If you divide it by Faraday's constant, that flips the unit from coulombs into moles. And then the reason why moles is so useful, once we're into moles, from a chemistry point of view, we can actually do something with it, because moles can be converted into mass. I'll say that one more time. Moles is a chemistry unit of measure. Coulombs is more of a physics unit of measure. So we have to try to find a way to convert a coulomb, which is a lot of electrons, into a mole, which is also a lot of electrons, but they're actually different numbers. If that makes sense? Once we can get into moles, moles is useful because then moles can go into mass. And that leads me to today's topic. We're going to talk about cell stoichiometry. We're going to be doing some stoic work where you're going to be using grams and molar masses, but you also have to use this formula as well. Does that kind of make sense, the whole point of today? Michael?
Even if the moles have, it's like the moles of electrons, because it can get the moles?
Yes. Yeah, because we're going to do some stoic work based on it being moles of electrons. Honestly, the best way to do this, I think, is just to hop into an example. So I'm going to do some examples. And if you guys want more than the 3 I have in the notes, we'll do more than 3. But. Okay, so imagine that we're thinking of the battery that I was using to run my clock for a little while. Okay. Let's say that we actually measured the amperage in that battery, and the amperage was measured to be 1.150 amps. That basically means that there is 1.150 coulombs running through that thing every second. And remember, a coulomb is basically just a lot of electrons. Rather than counting them one by one, we're counting them in a large group. I'm sure I wrote it down on a previous slide somewhere what it was, what a coulomb was, but you can look it up if you need. Well, if you run this thing for 1.25 hours, my question is how many electrons were transferred? So this one here is going to look something like this. I'm going to start with 1.25 hours. Okay, hours is not overly a useful measurement for us. So I might say something like this.
Breakfast? No, don't even bother.
Thanks, guys. Does this ratio make sense? There's 3,600 seconds in an hour. You guys know how I pulled that out? 60 times 60, 60 minutes in an hour, 60 seconds in a minute. Why is this useful? What cancels? Hours. Does that make sense to start with? Okay. Hopefully this kind of rings some bells as to how stoic works. Well, I now have an amp. An amp says there's 1.150 coulombs in a second. Does that make sense? Okay, well, now that has coulombs. Well, a coulombs is just a lot of electrons. So the last thing we need to do is figure out what is the number of electrons in a coulomb. We need to just find that number, which you guys would not be expected to have to do this. This is more of a physics question to kind of get us started, but we would need to know that ratio. If you had a physics data table, it would really help. So let me see if I can find my old one here. I'm sure it was in our notes, though, actually. It's got to be in there somewhere. Here's our notes from the other day. See whether you have those nearby, whether I can find that. Here it is. 1 electron is 1.60 times 10 to the minus 19 coulombs. Hopefully you guys maybe recognize that number from physics. And you guys are taking next year, we'll use that number a lot next year. So 1.60 times 10 to the minus 19 is how many coulombs are in one electron. So 1.60 times 10 to the minus 19 coulombs is in one electron. And let me just point out, you guys aren't going to do this on the diploma. I'm just doing this to get us started, okay? So, ooh, where am I going? There you go. So this will tell me how many electrons are transferred. Hours cancels with hours. Seconds cancels with seconds. Coulombs cancels with coulombs. I now know how many electrons there are. So, anybody have a calculator? 3 point. Just give me 1 sig dig. Actually, no, 2 sig digs. 3 sig digs.
2, 3, 4.
Okay, so we'll do that. Times 10 to the power of 22 electrons. Anybody else able to calculate that value? Okay, so we don't typically want you to do this. The reason why this is not useful is that doesn't help me. What we need is moles. Does that make sense? Moles is more useful because moles can be converted into grams eventually. So to just know the raw numbers of electrons, I mean, that's a crap load of electrons that just went through your wire, which makes sense, right? I'm expecting a lot of electrons. When electricity happens, a lot of electrons should go through your wire, right? So we're not going to typically do a calculation like this, but that would be how many electrons you have. This is where Faraday's constant comes in. Faraday's constant tells you how many coulombs there are in a mole. Because if we can convert not from coulombs to individual electrons, but if we can convert from coulombs into moles instead, then we can keep going with our stoic. Does that make sense? So what we're going to do typically is not this. What we would normally do is 1.25 hours. We'd times by 3,600 seconds over an hour. We'll times by 1.150 coulombs per second. And then we'll use the moles of electrons to coulombs ratio. And this is that capital F, that Faraday's constant, the 9.65 times 10 to the power of 4. Because once we get into moles of electrons, moles is something we can work with. That make sense? Okay, so let's try an actual example of what you might get asked on a test now, because that last one really isn't there. The kicker here is now I'm going to ask you how much mass of copper is there going to be. So we're going to run a battery for a while. I'm going to tell you how long we run the battery. I'm going to tell you how fast the electrons are moving in the wire. My question is, how much mass should you expect built up? Okay. So the key to finding mass has to come from moles, using a molar mass. So we're going to do a very similar process, but then when we're done, we're going to need to convert moles into grams. Does that make sense? So the first place I'm going to suggest we start is let's use that formula that I wrote down, because the formula is pretty useful. Moles of electrons is equal to the current that you have multiplied by time divided by that Faraday's constant. We'll start there. How fast do these electrons move? 12 amps. So that's 12 coulombs of electrons every second. So I'm just going to start by writing that. 12.0, that's how many coulombs happen every second. Then I'm going to multiply by time. Should I go with 40 minutes? Brad shaking his head vigorously. Why? We need seconds, right? Hopefully you can visualize the stoichiometry part of this process, as I'm going to need it to be seconds. So I could write this out like 40 minutes, but then I'm going to times by 60 seconds in a minute. See how now my seconds are going to cancel? My minutes are going to cancel? At this point, what am I left with? I'm left with coulombs. What is a coulomb? A coulomb is a lot of electrons, but it's not the right amount of electrons. It's like dozens. Oh, I don't want them in dozens. I want them in moles. So that's where Faraday's constant comes in. There are 9.65 times 10 to the 4. Ooh, what are the units again? Is it coulombs per moles of electron? Yeah. Coulombs for every mole of electron. What cancels? What remaining unit can I now cancel? Coulombs. What unit is left? Moles of electron is the unit that will be left. You know how in the last example, I told you how many just total electrons there were? And I think Brad, you told me it was like something to the power of 24. Rather than knowing how many individual electrons there are, it may be more useful for us to know how many moles of electrons there are. Because like I said, moles will eventually be able to get converted into grams. So I need some help with the calculator. Can someone help me with 12 times 40 times 60 divided by Faraday's constant?
0.298.
One more time, 0.298. That'll work. You probably have more numbers after that, so let's just save that value. Anybody else get that? Okay, good. So far, so good? So rather than measuring these things in a whole bunch of electrons Coulomb style, we're now measuring how many electrons we have moles style. So more of a chemistry unit. Well, now here's where the stoich comes in. If we have 0.298 moles of electrons, I don't want moles, do I? I want grams. But more specifically, I wanted to know how many grams of copper I would get. So the first thing I have to do is I have to change the unit type. I don't want electrons. I want to know how much copper there is. So I'm going to do a ratio. And I'm going to put electrons on the bottom and copper on the top. Can you guys visualize how that's going to cancel out your electrons? Here's our question then. How many electrons does it take to make a copper? The answer is 2. How did you figure that out? Yeah, look on the half reaction data sheet. Copper 2 plus needs 2 electrons to make a copper. Permanganate needed 5 electrons. Does that make sense? If you basically just look on your data sheet, like the one that Brad's holding right there, and just figure out how many electrons it takes to make something. Usually it's 1 or 2 or 3 or something like that, right? So you would say that for every 1 solid copper that you make, you need 2 electrons. So there's the stoich part where I've now canceled out my electron unit and converted it to copper units. Last thing, I've been alluding to this all day, we don't want moles, we want grams. So, like we've hopefully learned over the last, I don't know, year and a half of me teaching you this, grams over moles, that's what we need. That's a molar mass. Molar mass of copper. So use copper's molar mass, 6355. So take that exact value. So Michael, whatever you calculated, that 298, use that whole value, right? Times by 1 over 2, times by copper's molar mass. This will tell you how much buildup you should expect of copper. Anybody get an answer? Okay. Anybody else get that?
Yeah, I got it.
Okay, cool. So what that means is when we have a battery, you know how one of the 2 cells, I'm just going to draw them out here real quick. You have these 2 electrodes right here. One of these 2 electrodes should start building up in mass, and the other electrode should kind of start to dissolve. Well, now I know how much buildup to expect. That's what we're going to do tomorrow in our lab. Tomorrow what we're going to do is we're going to run a battery for about 10 to 20 minutes. And the electrode that's the cathode should start to gain mass. The electrode that's the anode start to lose mass. We're basically going to measure how much current there is. We're going to measure how long the battery runs for. So you're kind of going to sit there waiting, doing nothing for about 10, 15 minutes, 20 minutes maybe. And then when you're done, you're going to go to the back scale and you're going to weigh the electrode before and afterwards and see whether the amount of mass that it's either gained or lost is what we expect it to be. Does that make sense? Okay, let's try one more, then we'll take a break. These questions, they all typically look very, very similar. The only real twist you could have is I could give you time and say solve for mass. On this one here, this last example here, we're just going backwards. I'm giving you mass and saying solve for time. So we're just kind of doing a backwards process. How long will it take to plate 16.6 grams of chromium using an amperage of 3.9 amps? Okay, so do the reverse of what we did. On the previous example, we started with the current time in Faraday's constant. We got to moles of electrons, and then once we had moles, we went to grams. We're going to go backwards this time. So I'm going to start with grams. So do I want grams of chromium? No. Grams is not very useful. Moles is better. So mole per gram. I don't actually know this one on the mass off the top of my head. It's
52.00.
okay. Well, we'll go with what your data booklet says. That one's more precise, but go with the data booklet one. 52 right on the dot. Okay. So that gets rid of your grams. We now have moles of chromium. I don't want moles of chromium. I want moles of electrons. Does that make sense? So I'm going to use a ratio. So I'm going to put how many electrons I want on the top and how many chromiums are in the bottom to cancel chromiums. Now the question is, how many electrons does it take to make a chromium? Go to your data booklet. Find where solid chromium is being made and find out how many electrons it takes to make a solid chromium. Yeah. Most things are either 1, 2, or 3. Okay, why don't we calculate this number here? So if someone's got a calculator, help me out here. 16.6 divided by 52 times by 2.
0.638.
Good enough for now. So that's how many moles of electrons there are. So we figured out how many electrons we need to have run through our battery. Basically, this is a lot of electrons. The issue is it's this chemistry-physics overlap here. Chemistry measures things in moles. Physics measures things in coulombs. It would be lovely if it was the same number always. But they were developed simultaneously. No one figured out a way to make it uniform. The good news is all we need is Faraday's constant. So that's that 9.65 number. We'll use that to help flip from moles to coulombs. Okay. What I would recommend, though, is just use the formula I gave you. So the number of moles of electrons is equal to current times by time divided by Faraday's constant. That's the formula that was kind of given. What are we trying to solve for? Okay, so algebraically, how do you get time by itself? Times Faraday's constant up top and divide by current. So to find my time, it's going to be my moles of electrons times by Faraday's constant and then divide by my current. So let's give it a try. I now know how many moles of electrons I have. 0.638 blah, blah, blah moles of electrons. Faraday's constant is basically the way to flip between chemistry and physics ways of measuring. So 9.65 times 10 to the 4. That's how many coulombs are in a mole of electrons. Hopefully you can see it. You see how the moles of electrons are going to cancel? But we don't want coulombs. Coulombs is how many moles. No, coulombs is how many. No, that's not what I'm looking for here. Amps is the last thing I'm missing. Because I'm missing this I number down at the bottom here. I is current. See how it says we use 3.9 amps? 3.9 amps means that we use 3.9 coulombs every second. Can you guys visualize now how the coulombs number is going to cancel? What unit is left? Seconds. So take that number that you calculated times by Faraday's constant and then divide by this. It should give you how many seconds you have. You got something? You got seconds? What do you got? Okay. 15,000 seconds. 15797. Chances are, when they ask you this question on the diploma, they're going to convert it into something else. So I would say divide by 60 to get it into minutes.
It's 4.39 hours.
Or divide by 60 again and make it 4.39 hours. Okay, cool. You guys are well ahead of me, it sounds like.
SigDig's make that 4.4?
Yeah, we should do SigDig still, though. Yeah, 4.4. Thanks, Brad. Good catch. Did that make sense? For some of you guys who I know I taught physics to, it should really feel like you're doing physics right now. Because you kind of are. You're using physics formulas combined with Stoic. Hence the term cell stoichiometry. You need to do a little bit of Stoic work where you convert moles into grams. And then once you get good at that, it's a bunch of formula work after that, where you just need all your units to cancel. So I'd say the two most common things you have to do, I'll give you a mass, you solve for time, which is what we just did, or I'll give you a time and you solve for mass. And that's what we're going to do tomorrow. So tomorrow's lab, be prepared to be a little bored, because really you're going to hook up a battery and you're just going to let it run. And you're just going to use your watch. You're going to time out like 10, 15, 20 minutes. You're going to measure the current. And after 20 minutes, you're going to go weigh your electrode. It's either going to weigh more because it's the cathode, or it's going to weigh less because it's the anode. We're going to calculate how much difference in mass there is. And ideally, that difference in mass should be what you weigh there. Sound good? Cool. Okay, that's my lesson. I think we're done. Any questions? Yes, sir. Okay, we'll take a break. When you come back, I guess work on your assignments, print off tomorrow's lab maybe. We're done the unit. Yes, we're halfway done Chem 30. Halfway done Chem 30.